right. Thank you again for staying with us, and I'm really glad that the microphone is no longer here. Let's see. I'm going to continue with this assumption that everything is complete. That just means that implicitly in the spectrum, I'm always going to imagine the completion of that spectrum, and I will continuously write these P completions. The way we always like ours that in the infinity ring, or from it's much less structure than that, we can form this PHH. Explicitly is R essence of Z off or over the sewer spectrum. And this comes with a lot of structure. It is an E infinity ring, and obviously by its construction, but it also comes with the conditional structure. And this comes with the seeking to the infinity action. So again, when your P completes, there's not a substantial difference between the circle and the Z mod P to the infinity. So I will just think about this as a compatible action of P power cyclic groups for all powers of P. Together, and equivariant Frobenius map from the to its geometric fixed points. And this is just a fancy way of writing the tape construction, because I'm taking THH to be a Borel CP to the infinity equivariant spectrum. However, as we discussed a little bit last time, when resolving THH, in order to talk about, say, a motivic filtration on it, it is very helpful to allow resolutions by things that are not necessarily Borel CP to the infinity spectra. We will allow resolutions by things whose geometric fixed points are not equal to the plate. But THH itself, we'll just set the geometric fixed points equal to the plate. And then we have this construction TC. TC and R with the fiber of two maps, one of which of the Venus map, the other is called the canonical map. And of course, these geometric fixed points. Okay, so this Frobenius map is just the fixed points of this structure map. The canonical map comes from first taking CP fixed points, noting that CP fixed points always map to geometric fixed points, and then taking the residual action. Okay, so that defines TC. And then last time we discussed that if R is reasonable, usually if it's discrete and bodies symptomic, that more generally, we define motivic filtration and CH and R. And we defined it by resolving by more general things with these structures, where that resolution was required to have even homotopy groups and even cells. And this reasonableness condition is about the existence of such a resolution. It's not guaranteed that we could find something with even cells and even homotopy group, but when we can, we get a motivic filtration. And because we're resolving by things that have all this structure, this induces a motivic filtration on TC. In particular. Okay. So then associated graded. There's star nodes. You are. It's called symptomic homology. So in terms of the talk this morning, everything here is p-completed. So I'm talking about the symptomic homology of p-completed rings. And if I were talking about more general rings, I would have to do something not involving TC, but involving gluing TC to some metallic homology. But for me, everything will be p-completed, and symptomic homology will just be the associated graded of this motivic filtration and topological cyclic homology. All right, and then just to remind you a little bit of the first day, what sort of things can we hope to understand or observe about this symptomic homology? And let L be a p-adic number field. Something like EP with ring of integers. Well, and our comparison theorems tell us that if I take the homotopy of this associated graded, you see that it's ring of integers, and mod out by p and invert p1, that this will be some bi-graded FP adjoining v1 plus minus module, and it's going to be the same thing. Let's see. Galois homology with the number field coefficients and various two twists. These are both bi-graded groups. All right, so when we plug in OL, this symptomic homology has a very nice interpretation. What is one of the most basic facts about Galois homology? Well, one basic fact is that this transmitters anti-gravity in the form of this local taped body. So it's not perhaps immediately clear from this definition, if you like, of Galois homology is some strange thing involving PC that should satisfy the duality. There's a question explicitly asked by Sumi and Rognitz around the year 2000. It's related to integers. Those pi star, their star nodes. We see the complex state theory, mods and power of P and some power of V1. We feel very good. Satisfied home radio. Is this group self-dual, say in a compatible way as A and B varies? And when they asked this question, this motivic filtration did not exist, but ignoring the fact that this was supposed to be bi-graded and just viewing it as a singly graded object, it appeared to satisfy Poincare duality, at least when A and B were one. And so they conjectured that this should be true for general A and B, and then it should be true with the motivic filtration. And nowadays, using that language, when we have a motivic filtration, this question is a perfectly well-defined question. So what I want to do today is sketch complete sort of data. Proof of this question, this conjecture, answers yes. And this was developed from discussions with Sanoff and and dimensional ones. And when I say direct proof, I'm going to give a sort of, if you like, computational proof of this kind of thing. And then maybe tomorrow I'll get back to defining some categories that might participate in the 600 formalism sort of proof of this thing. But when I mean direct proof should still work for a variety of things, not just complex state theory. It should work for any higher local numbering, whatever that in higher here is in the sense of chromatic homotopy theory. So in particular, I want to prove duality for sort of a uniform manner for any ring of integers. So reprove tape duality in the classical form. Want to kind of for you. And it'll be Hahn summary for you. Team up. At least these kinds of rings. And here I'm meaning these to be at any prime. So in particular, I look at something like a TMF at a large prime that can be a somewhat complicated, complicated ring from the point of view of asking how to name V1 and V2 inside of it. Okay, so let me highlight some features that these rings have in common. And I will use these features, but some of them may very well be possible to remove from the story. Part of the question here is what is the fully general class of B that we should be studying? Maybe not immediately apparent, it should count as a higher local number ring, but at least these should be examples. So each of these B's has the following properties. First of all, this connective with I0, a ring of integers in some key and number field. Question about, let's call the residue field here. Okay. Okay, with some finite field. Then because phi 0 of B is a module of a B, so is K. K is also a module of a B, and the key condition seems to be a K perfect U module. K can be built from B in finitely many steps. I'm going to use maybe just for convenience, K has even cells as a K tensor that would be the module. Okay, maybe a somewhat strange condition, but one that's satisfied in practice for all of these examples. And then I'm going to use that the mu homology of the is even and quasi-symptomic. So the mu homology of equal even means in particular that it's just a classical commutative ring. And forgetting about the grading, I could ask, is that classical commutative ring quasi-symptomic? That's true for these. And let's see. I want that there's an integer n. That P with Bn is a regular sequence. Any homology of B and Bn plus 1 is 0 among the previous ones. And finally, I'm going to ask that there exists historically S module B And I mean a perfect first study as model, so something built out of the sphere and finitely many steps, such that so first star of B, well, this is this motility associated graded, is in the fixed subcategory. This last condition, you're supposed to think of V as something like a Smith Noether complex. So if I take KU and I mod out by P in V1, I don't get FP. I might get FP adjoining some powers of the bot element up to the P minus first power of the bot element. If I tensor a Smith Noether complex with KU, I might not literally get a finite field, but I'll get something that is built out of a finite field and finite in many steps. And, I want to exclude things like polynomial rings in a single variable that is unrelated to any of the VIs. So I want the extra variables here to be VIs, and one way of capturing that is to say that there's an actual finite S module that reduces you to approximately the ground wood. All right.
Because that's perfect. Over curve.
Yeah, a little bit correctly speed. So you have to be a little bit, I mean, if you really want to handle cases like KO, this is telling you you also have to mod out by eta because eta might not be no code. What?
How can you take something? Or is it?
So maybe let me just say at least these things they satisfy these properties. This is roughly the only properties I will use. And I'll just say that it remains somewhat in flux what the appropriate definition of a higher the number of things should be. I don't even necessarily believe that you need all of these properties. Oh, yeah.
Does this they were trying to show so one variability for that thing imply one variability for this like V1 version of that?
Yeah, so the Poincare duality statement we're going to prove involves this n, right? There's some n here that is telling you a height.
So generalize both.
And it will directly generalize both. In particular, I will tell you all the ingredients you need to prove that this thing is a Poincare duality algebra if you never knew without Galois. Yeah.
Okay, so that last condition is that new one you've now added.
Yeah.
Relatively different. Is that going to be needed or?
Well, it's needed to move from THH to TC because, for example, if you want to sort of take K coefficients in a way that's compatible with circle actions, you replace taking K coefficients with tensor. There's more general duality statements for THH that this recipe is essential. But you don't really expect this to work if you took TC of a polynomial ring over FP, you know. So you need to somehow say that the extra variables you're adding are related to the VIs.
You push up the back blackboard when you think it's here. Just if you push it up so we can see both of them, if you think
I was almost good enough.
yeah, that's great.
Okay. Right. So
explain why you need a function that K is quantum.
well, I mean, you know, I think it's just not true that our cohomology of infinite fields satisfies Poincare duality. Oh, okay. Even classically. All right, so what's the main result? Okay, so I find a claim that if I take the homology of first notice and TCOE. That I can find some integral. So this is some function to the Brown common stabilizing thing, so it's like picking out the top class. And the claim is that if I do this, this should be a mod Vn plus 1. Where Vn plus 1 might refer to some power of Vn plus 1 here. So there's this diagram. I've only drawn in one map such that the integrals make the source on the value. In particular, I'm saying that with this ring satisfies Poincare duality, where this is some choice of what it means to pair with the fundamental class. That I have a little bit more to put in, but I can skip this to just star, and I can convert the filling. And the plan is that there exists a unique integral here. So a unique way of making this diagram commute so that this also becomes a Poincare duality algebra. So this is the Tate duality statement that, for example, generalizes simple Tate duality. But we're pulling some maneuver, which is a little bit common when working with the TC. We're proving something about what happens when you mod out by Vn plus 1, and then introducing what happens when you invert Vn plus 1.
Sorry, so
Duality statement. Yeah.
Notational question. What exactly do you mean by like B star of the associated gradient? Just to
So I just mean take the, which is a Gerst-30S module, answer it with this, and then take pi star. Now, probably, you know, it would certainly suffice us to think that this is just some Smith-Toda complex. This is just modding up by some number of these guys. For most of these. So there's sort of a few things one has to do, but maybe the first thing is to construct this integral that's not the dashed line, and then we're going to try to prove that we have a Poincare duality group. But to construct the integral, you can actually do something really simple. I'll just mod. It's a there will be a pi degree of this thing. So if you look at the pi-graded groups, there's one that's going to live in the largest motivic filtration and the largest stem. And what we're going to check is that there's going to be something in that top pi degree. And this class in this top pi degree, we have Rho plus B, a copy of FP in that pi degree. So that's what we're going to prove. And that tells me what the integral is up to an element of FP cross. So usually think that the Poincare duality is given by multiplying elements till you get to some top pi degree. And then you're just checking what multiple of the generator of pi degree you get. That it will be clear what the integral means as long as we can compute these groups, because as long as we see a single FP in a top pi degree, that determines the integral up to an element of FP cross.
Sorry, just maybe I space for a second. Could you tell us what I is?
The I is
Like in that second. The I.
oh, that's the Brown commons dualizing split.
Okay.
Okay, all this stuff about Brown commons, whatever, if you aren't familiar with it, I'm simply saying it all translates to saying that I want to compute these groups, and there's going to be a top group, top motility filtration, top degree, which will be just the copy of that. And this FP is arising as the Frobenius covariance of the finite field K. So it's actually an FP regardless of what the finite field is. Okay, so if you don't like integrals, really we just want to complete this. And then maybe another remark is that this we did dash point value automatically solve it. Perhaps I won't go into this in too much detail, but if I can prove that that this group, that this bi-graded group is Poincare self-dual, it just automatically implies the result where you invert the n+1 instead of kill the n. Consequence of this way too long ago. So really, I want to focus on trying to explain how you can prove this quotient is Poincare self-dual, which is just the calculation of this single pi degree. So I want to produce the class in here and then check that this class I'm producing defines the new Poincare duality object. But one of the main things to do now is to produce an FP in this top degree. And the way in which we can do that is to observe that a perfect P module is transfer map. I'm drawing that map from PC okay to the TC of P. And I take lead and one plus one star coefficient. Claim is that the polarizing class in the top pi degree is in the image of this map. The image of this instrument. So that shows you that there's that defines a dualizing class. In order to define an integral, you need to show that that dualizing class is non-zero. And that it's the only thing that is in that top 5 degree. But in fact, then the Lichtenbaum-Quellen property helps here. And then it's non-zero. The only thing. So maybe I thought to sort of make this statement more reasonable, we could see how it works in practice in the case 1b is this atom summand.
Sorry, could I ask just if I'm following correctly?
Yeah.
So you're using the last property you just erased, sorry, but the answer with B is a perfect module over the very even of the sphere where you it's a thick subcategory generated by K.
Yeah.
And so you're
Well, just the fact that K is a perfect B module.
no like already just for this remark that it's enough to find the top by degree. You're using this property and then say basically you're just showing it's enough to find like a orientation class that's automatically dualizable and dual function that class. That's the logic where it's enough to find the
Well, maybe. So there's I am claiming that it's enough to disprove the top by degree is an FP, and it is. When I'm saying stuff like the Lichtenbaum-Quellen property, there I'm used the fact that that property holds is related to the fact that you can get down to K when approximately when you tensor with B.
yeah, I guess I was just already just about the solid integral, why it's enough to get
Oh,
find this class.
I mean, we're going to define class, and to define the class, it's enough to define the integral, it's enough to define the class. But then after defining the integral, I have yet to mention how you prove that induces a duality, which I hope to discuss. There's two problems. One is defining the integral, and the other is proving it's defining duality. And just to define the integral, you have to just make a calculation of these groups.
So if your assumption is that we should use some numerical star even sphere module, and we just assume that it is like from the Taylor solid homomorphically we have some modification.
Okay, you'll do fine just assuming it's a Smith-Toda. For various more complicated things like KL, we might need to mod out by other elements beyond just the units. But let me
should assume that it has some multiplicative structures.
let me explain how it works for the atom summons kind of completely. And I think at least to me, especially because this is supposed to be a free 6-monthly talk, maybe the point is just to get some examples completely explained. So the main example is maybe the atom. Okay, so how would the THA to L, we have three coefficients. So that that's polynomial on some two exterior algebras, exterior generators, this and this is the same thing as the equation to help modeling out by P and Q. Right, so the V here will be let's start the S mod P1. And taking FP coefficients is just the same as modeling out by P and V in this case. All right, but on the other hand, we could look at pi star. At pi star nodes at PHH and FP, on P and V one. With the same coefficients. And this is a little bit funny because before I mod out by P or V one, I get the polynomial ring and characteristic P. So I'm just modding up by 0 twice. So this is simply FP applying to 0. That's an exterior algebra class assignment for epsilon V0, epsilon V1. These are classes that are responsible for Bach-Stein spectral sequences for telling you that P and V1 were already 0. And so the claim is that the transfer map means product to this pattern. You can check for yourself, for example, that the degree is lined up to make that possible. So how can you prove that? There's a variety of ways you can try to make this calculation. One way is using this formalism of log THH, which is a convenient way for computing these transfer maps. Another way you could think about this is by thinking of L as atoms filtered. So it's thinking of L as FP adjoining V0, V1, and then in using that filtration, you can reduce to understanding transfer maps between just FP algebras, which is more classical.
Sorry, could you remind me where the transfer? I mean, just because K is a perfect P module, is it obvious where it's not? Why do you understand?
So that tells you that if you have a perfect K module, then you in particular have a perfect P module. So that gives you a functor of categories to which you can apply something like THH or TC.
Yes.
Degrees not oh, yeah, sorry. I think I needed a power here. Okay. Thank you. It's very important. Okay. I don't know. Is there like a light that is not?
Yeah, it's a light which is not on. Where's the light actually? It's up.
You got it.
So you have to make some calculation of this transfer map at the level of THH. But then let me explain how just knowing this transfer map at the level of THH can tell you something about TC. There's a diagram. The TC of FE. And that transfers to the TC of line and mod off by PD1 and PD2. So this object where I additionally mod out by V2 is the thing in which I want to produce the top class. This is the thing I want to prove as a dualized class. And so this maps to this rotation FP1, and this maps to this what am I saying here? V2 is 0 in this object because this object is a L algebra. In TC, V2 is not 0. And then here we are supposed to know that this class maps to M1 and M2. And what we will prove is that lambda 1, lambda 2 is in the image of this map. In fact, in the image at the top now. And that produces our dualizing class, which is actually partial times lambda one lambda two. Notice that means, but the big tricky thing is to show that lambda one lambda two is equal. And it's that. And it's a little bit interesting because if I didn't mod up by v2, this statement would be false. Well, on the bottom is true mod p v1, but when I go to tc, I need to mod up by v2 for the statement to be true. And the point, if I look at tc of fp, it's isomorphic to ZT plus 1 minus 1 ZT. And it plus 2 is equal to 3. Equal 0. So if I take TC of FP and I mod out by P v1 v2, what I get is an exterior algebra on a class partial Hahn bar and v2. So this class, this suspension I'm just denoting by partial. But if I mod out by P, these become two FPs. And then when I mod out by V1 and V2, I introduce exterior generators. So that I get 0. TH which is FP. On P and V1. Instead, FP adjoined. 0, epsilon equal 0, epsilon 1. And then the map from TC to THH, and that map sends epsilon 1 bar to epsilon 1 minus 0 to epsilon 0, epsilon 2 bar to minus 0 to P. So this map does something interesting. And that's kind of the point. But I would just like to indicate that in order to prove that lambda 1, lambda 2 is in the image of this top map, we need to make a calculation, the bottom arrow, which is a THH calculation, much easier than a TC calculation. And the other thing we need to do to lift that to TC is understand something about this map. But this map is just about FP, it's not about the atom summation or some strange ring spectrum. Right? We're just making a calculation about THH of interesting ring spectra and TC of fields. And so this calculation, by the way, you can make by observing that this map is compatible with power operations. Okay. So that's a little bit about how to produce the fundamental class. And to finish this sort of concrete proof of concretality, I need to demonstrate that I get a concretality algebra using this fundamental class. Maybe I should say just a bit about how concretality works classically. Usual theorem of W is a M, so it's like a closed oriented manifold. Fundamental class And then I can take homology again, and coefficients. Multiply together. There against the fundamental class. And the perfect pair. Classical, but I wrote it up to on the board, maybe to contrast it with a slightly less classical theorem. Which is and sometimes called Lefschetz duality. It's probably be a compact oriented n plus one manifold with boundary. And fundamental class now. One class in the homology, relative homology. Like W with its boundary closed up to a point to give you an actual closed manifold. Then what is the form of Poincare duality in this kind of situation? We get the following sequence of the homology W acts comically to the homology of the boundary. The boundary Poincare so pure. And if I call this my alpha, the right boundary is 0 of alpha. Linear rule. And the claim is that this is so this is this Lagrangian property that was highlighted a little bit in the first lecture. With this sitting inside this self-dual thing as a Lagrangian, and that's the form in which Poincare duality for manifolds with boundary works. All right, so now.
Where did you use the fundamental class?
Good question. I think I'm just using it here. In self-duality with boundaries. Right. I wanted to write down something because there were so many questions at the discussion session. What is this meaning? Why is this word Lagrangian being used? And the real answer, of course, that's the word Bargot-Bot used in stuff. So, right. So, oftentimes when we're thinking about a manifold, we can imagine cutting it up according to some handle body decomposition. And there's a sense in which the Poincare duality statements glue along with the handle body decomposition. But if we're going to glue Poincare duality statements, we have to understand the manifold of boundary, which will appear when we glue things. And so let me draw a appearance. My ability to draw cartoons may be questionable. I'm drawing a donut with two cylinders, right? And then there's a single cylinder here. And one way in which I could get a torus is by just taking these two cylinders and gluing them together via two maps from the cylinder into the bigger cylinder. So we could imagine just using these two maps, gluing their images together and getting a closed manifold. And I want to attach names to all of these things. So here I'm going to write T sub minus L E. E1. And E2 divided by A1. So then I'm gonna write E. Yeah, I'm gonna write maybe I'm just gonna be acknowledging. And here I'm gonna write let's see, nice about the pyramid TH. Okay, sorry. So this is the things I want to write. So thinking of this TC minus on PV1, P2 as a cylinder. So it's a compact manifold, but it has a boundary. This TP is maybe if you thought of it as some thickening of a circle, and it has it's actually to be thought of as a compact manifold, of maybe lower dimension than TC minus, and then this is a a closed submanifold of a smaller dimension, and all right, so this is this whole cylinder. But this closed piece breaks the whole cylinder into two smaller pieces, right? And the smaller pieces with TC minus of L, P, V1. Here's one of the smaller pieces. And here's the this one. All right, maybe I finally got that correctly on the board. I apologize for being inspired to say something about in terms of manifolds for the questions, but here's a picture of some manifolds. There's a way of decomposing TC into these pieces, right? So if I take TC mod PV1 V2, that comes from gluing TC minus mod PV1 V2, which is this whole thing, to TP mod PV1 V2, which is this piece. So you glue this along the Frobenius and canonical map, but I want to think about TC minus mod PV1 V2 as broken up into three pieces. Okay, and then there's some theorem, which I think in the nanocode literature is called the Walls gluing lemma, which tells me that the Poincare dualities for all these pieces that we're cutting in this manifold are continually relate to one another and glue together. And so Poincare duality we see it like PV1 V2 is a combination of statements. And the first statement is that P of L on PV1 V2 self-dual. They have some duality. The second statement is that PH of L my PV1 might be PH of L my PV1 mu plus PH of L PV1 mu inverted is the lambda. And the third statement is that TC minus of L mod P1 happen to TC minus Let's see. Let's see. So, to the extent in which this is not botched, this I'm trying to say that we can prove Poincare duality using the fact that TC is glued out of TC minus and TP by proving a bunch of individual Poincare duality statements about smaller pieces. So I'm trying to reduce some statement about TC to statements about THH, TP, and those kinds of friends. But this statement I actually proved for you on the first day, because this is exactly that statement that something involving THH with FP coefficients for the Lagrangian. And this is actually isomorphic to THH of inverted. That isomorphism tells us that we get self-duality of this object again because we're related to something we talked about on the first day, which is a duality statement that's solely about THH. And the last thing is this Lagrangian statement. But again, at least these two pieces are now directly related to the things involving THH. The duality part of the Lagrangian statement is something we learned about on the first day. And let me just end with one lemma to convince you that it's really this duality that's the interesting feature of this and not the Lagrangian statements. The Lagrangian statements are much easier than the duality statements, even though the duality statements are pretty easy because they only involve THH. There's a probably correct picture of this on Robins's website.
So the geometric, so you have the abstract definition of Lagrangian, and can you see? I mean, how is that reflected in that picture?
So it's supposed to be the Poincare duality statement for this half cylinder, which is a Lagrangian statement, and then there's one for this half cylinder. And those are these two Lagrangian statements. And then they're glued along this manifold, which is this self-duality theory. Okay, again, there's a picture of this on Robins's website, which is probably more appropriate than what I'm drawing. But I wanted to indicate that the duality that you need all happens at the level of THH. And there's one additional thing you have to check, which is about a Lagrangian statement, which is not purely happening at the level of THH. But in fact, it's a very general fact that if R is a ring, D is an element in that ring, and there's a diagram are my outing elements and vector elements. And if I have two integrals such that their restrictions become the negatives of each other, making non-positive ones. And the inverse Poincare duality of those. Then this map is Lagrangian. So this is just a super general fact that you get a Lagrangian. And this subtle point is just to prove that these are dual, and you have to check that the integrals defining the duality are compatible back in line. So almost all of the things to check at once occur just in THH. All right, next time I'll get back to some more totally different stuff.